is Professor Yuri Tschinkel from Courant Institute of Mathematics at the NYU, and the head of Physics and Mathematics section of the Science Foundation. Thank you very much for coming, especially to talk to us.
Thank you. Delighted to be here. Okay. One more minute. Here we go. It's about fields. Fields are sets with two operations, addition, multiplication. Our favorite fields, Q, R, and C. And the field automorphisms are simply mapped from here to there, compatible with the structures, and that's a group. And the rationals don't have very much that you can do with them. Now, so of course we have the complex conjugation. It leaves R invariant. Now there are also cyclotomic fields. You can add roots of unity. You just adjoin the root of a minimal polynomial. Piece root of unity. It's a vector space, and there are automorphisms. And the automorphism group is well, additively Z mod p minus 1. It's a multiplicatively Z mod p multiplicative, and of course standard applications. And this is sort of the beauty of the thing. Gauss realized you can construct regular p-gons with corpus and rulers. 13 does not work. 17 works. Why? Because 17 minus 1 is the power of 2. Okay, and so the message here is that there are hidden symmetries in geometric shapes, geometric objects, and we'll be exploring some of those symmetries. And it's, of course, a major theme in algebra and geometry. Now, assume that we are over some field that contains piece roots of unity. Now, we want to produce an extension of this field, Galois extension, finite vector space over that in the field structure, with a prescribed Galois group Z mod P. And so Kummer's theory tells us that actually we can parameterize all such extensions by elements in the multiplicative group of K modulo the piece powers. And we're going to take a piece power of an element in the ground field, and the Galois group will act on it by multiplying with the piece roots of 1, including the trivial root. And how do we prove this? There is something in the background, Hilbert's theorem 90, some statement about Galois cohomology. I won't give you the proof, I give it classes, but again, some symmetries relevant, and this way you can produce, Z mod P actions. What we'll be looking at are automorphisms of more general extensions of the field. In particular, we'll be concerned with the complex numbers as the ground field. The complex numbers surely contain all roots of unity. There are no algebraic extensions over it, but there are interesting transcendental extensions. So we'll call a field rational if it's a purely transcendental extension. We just add independent variables, and there's nothing else to this. And stably rational if it becomes rational after you add a few independent variables. So those are key notions that have been studied in field theory, if you like, in algebraic geometry. So these are of particular interest to us. Why? Because those happen to have, very interesting huge groups of automorphisms for n bigger equals than 2. And the study of these automorphisms has been a major theme for at least 200 years. So how that connected to other things? Well, just to recall, the projective algebraic variety is just a solution of a system of homogeneous polynomial equations, many variables, many equations, with coefficients in your ground field, let's say complex numbers. Basic example of the projective space, and another interesting example of the cubic surface. And so we want to understand how close is anything that's given by equations to something that doesn't have any equations at all, like projective space. And how close means in this language, are we birational to projective space, or are we stably rational? That is, if you multiply with projective space, then you become rational. And this reflects the property of the function field of the variety. So for projective space, the function field is just a purely transcendental extension in the corresponding number of variables. But for more interesting things, well, we have to figure out. And of course, rationality implies stable rationality. Now, This is geometry over fields, closed or not closed fields, but parallel to this story, there is geometry in presence of group actions. So let's start with smooth projective varieties of the complex numbers equipped with an action of a finite group. There are also many interesting examples here, some infinite group effect. But let's look at finite groups first. And we'll say that the action is linear if the variety together with that action is equivariantly birational to, well, we want to say projective space, but we have a group action, therefore equivariantly birational to projectivization of some faithful representation of our finite group. And stably linear means that you take a variety, we multiply with Pn, we are in the context of group actions, trivial action on Pn, and we want that to be birational to projectivization of linear representation. So those are the key notions in this business. And of course, trivial case, G equals 1, there's no action at all, it just reduces to the previous question. So linear implies stable linear naturally. And the reason I put it up like this in parallel is because there are actually deep connections between geometry over non-closed fields and equivariant geometry. And the talk today is about some of these connections. I want to highlight this. Now, let's start with similarities. So when we see a non-closed field, we think about the Galois group. The real numbers, the absolute Galois group is Z mod 2. But over the rationals, it's a big group, profinite group. So let's look at the absolute Galois group gamma k. A smooth projective variety over our non-closed field. It has a function field. And of course, the Galois group will act. It will act on, well, everything that's defined over the algebraic closure, special loci, geometric Picard group, Brau group, and so on. Now, let's say we have a G variety over the complex numbers now. Then G will also act on the Picard group, on Brau group, on everything. There is a cohomological abstraction to stable rationality of varieties. That is, again, we compute H1, absolute Galois group, acting on Picard over the algebraic closure. And if it's not 0, well, then we can't be stably rational. And there is also an abstraction to stable linearizability, phrased in the same language, namely, if for some subgroup of our group, the H1 G prime acting on PIC, the Picard group of the variety is non-zero, then we can't be stably linearizable. Now, what are the differences? You see, if you have a rational variety, if you like projective space has many rational points that are all over the place. And so a rational and a stable rational variety has rational points. But if you look at the G variety with some non-abelian group acting, well, it could be empty, or even with an abelian group. The set of fixed points could be empty, and the action could still be linearizable. For non-abelian groups, you have linearizable actions with no fixed points. Moreover, existence of fixed points is not an equivariantly birational property. You can start with fixed points, blow up, and lose the fixed points. And this, of course, never happens when you work over all those fields. If you have rational points, you blow up, you blow down, it's a birational property. But it's actually worse than that. When you think about projective spaces or non-closed fields, there's only one, your standard projective space. You think about projectivizations of G representations for groups G, it turns out, and this will be the message today, there are actually non-birational linear actions. And that is, how to detect this and so on and so on. That's the topic of the talk. A word about cohomology, since you've seen it already on a few slides. Well, if you want to compute this thing in the context of non-closed fields, what do? You take a cubic surface, you write down equations of your 27 lines, you see what the Galois action does on those, and then you compute. It turns out that in the G equivariant context, it's actually much easier. You don't need to look at those 27 lines. You only need to look at fixed loci for the action. And the recent theorem, relatively recent, by Bogomolov and Prokhorov says that, let's look at a special case. There's just one element acting, suppose of prime order. If that has a fixed curve of genus at least 1, on that surface, rational surface that we're looking at, then H1 G Picard is going to be Z mod P to the 2G, where G is the genus of the curve. And Schindler generalized it from prime orders to arbitrary orders, and then Lucretius and I last year figured it out for all finite groups acting on rational surfaces in terms of fixed point loci, not in terms of these exceptional curves. There is some coupling, of course, there, but well. Now, so the generalities. Let's look as always by dimension. Let's look at curves. Birational curves over any field are isomorphic. So if you want to understand birational automorphisms, well, then the Cremona group, the birational automorphisms of P1 over K, it's actually the automorphisms of P1, which is PGL2. Okay. Now, of course, if you want to figure out what kind of finite subgroups connect on P1, well, cyclics, dihedral, A4, S45, and we've seen those before. So, well, there are these platonic solids, symmetries of these things. We heard a beautiful talk yesterday about symmetries and so on. Well, how do you think of that? Well, it's on a sphere, P1, complex numbers, anyway, you see these parameters. Now, you'd think, oh, well, this is done, you're done. But what about arbitrary fields? Now, if your field is a subfield of the complex numbers, and of course, symmetries that are under complex numbers, some of them will also be, definable over your field. And so there is a characterization, the cyclic group and the dihedral group will be contained in PGL2K over your enclosed field if that combination of roots of unity is in it. Now, how about A4 and S4? Well, here the condition is that -1 is the sum of squares. How about the next one, A5? You want the -1 to be sum of squares, and on top of that, you want 5 to be a square in your field, which is not always the case. All right, are we done now? Well, it turns out, well, there are other fields. How about positive characteristic? And this is a relatively recent paper by Bouville, who tries to untangle this in positive characteristic. And under the assumption that the characteristic has nothing to do with the group order, well, first of all, if you have a closed field, then isomorphic subgroups are conjugated in the automorphisms. Already a good sign. But what about non-closed fields? So, well, it turns out that for some groups, there's only one conjugacy class. All right? But if you want to understand involutions of a non-closed field, then those conjugacy classes are parameterized by potentially a huge thing, K star or K star square. Everything modulus squares. This is like commerce theory that I mentioned. There is a similar description for Dn, and there is something completely worse for C2 plus C2. Because not only you get K star over K star squares, you also get the Hilbert symbol into the picture. Okay? This is just a side remark, but this is to tell you that even that completely straightforward question, subgroup of PGL2, well, anyway. Let's go to surfaces. The classical theory, 19th century, early 20th century, classical Italian algebraic geometry tells you, everything of the complex numbers rationality is equal to stable rationality. Over non-closed fields, however, this came much later, that equivalence can fail. And how do you do it? Well, there are basic things that you can do with surfaces, blow up, blow down, and to show that there's some algorithm that will reduce you to Delpezzo surfaces or conic bounds. And your favorite Delpezzo surface should be the cubic surface. And the second favorite should be an intersection of the quadrics and P4. Now, over non-closed fields, the rationality problem is completely settled. All you need to know are the rational points on that surface, first thing. And second thing, is the Picard a permutation module, which means that can you take these exceptional curves, 27 lines, and find Galois orbits consisting of disjoint lines that you would then contract until you get down to P2. All right, so this is settled. So you just look at what the action is. You can effectively write down the equations for those exceptional curves, and you go from there. So in particular, since it's a permutation model, that H1 thing will be true. How about the stable rationality problem for surfaces? That is still open. And the conjecture is that it will be stably rational. I wrote rational here, but it will be stable rational if and only if the rational points are there and the Picard is stably a permutation module. Not on the nose necessarily, stably. You add a permutation module to it, and then it's a permutation. Now, okay, that's at least a conjecture, and it's wide open. People have been trying for 40 years, and so on. Now, how about G surfaces? So in the G surface situation, you can look at those of degree less equal than 4, like intersection of two quadrics or a cubic, and so on. You assume that you have, a regular, generically free action of G, and you assume that it satisfies this cohomological condition. Then let's assume we are not in a situation where your surface is equivariantly birational to P2 or P1 times P1. Well, then what happens is there is only one such thing, and that's the thing. And whether or not the thing is stably linearizable is open. So that's a conjecture. This action, so intersection of these two quadrics, completely symmetric, and the group, as you can see, there is not much to the group, but try to untangle this invariant theory with everything at your disposal. So this is degree less equal than 4. Then you can ask, well, what about degree 5, degree 6? The bigger the degree, it turns out, the easier the thing. The easiest thing is anticanonical degree 9, P2. So in a paper from this year, 22, Brendan and I essentially settled the stable linearizability problem for the Delpezzo surfaces of degree bigger equal than 5. And so the punchline here is that there exist nonlinear but stable linear actions in degrees 8, 6, and 5. 7 is not interesting in this business. 7 is always equivariantly birational to something else. And we have a complete answer for quadrics, P1 times P1, and also in degree 5. Quadrics, you also have non-linearizable but stably linearizable actions. Okay, so we've seen that this is kind of interesting, but what is the group of birational automorphisms of P2? Well, there are, of course, linear actions, elements of PGL3 and over a non-closed field. As we have seen, you can have all kinds of things, especially positive characteristic. And then there is one more. What you can do is with x, y, z coordinates on P2, you can look at 1 over x, 1 over y, 1 over z. Now, when I write it like this, I'm asking, well, okay, so for almost all x, y, z, it's of course defined, but it's not defined when x is 0 or y is 0, z is 0. So that means that this map, it's something that you see on the function field, but you can't realize it on P2 itself. It's not a regular thing on P2. It's a birational involution. Okay? Well, and it turns out that the linear ones and this one, Cremona involution, generates the whole birational automorphisms of P2 over C, algebraically closed field. Now, okay, you'd say, well, we understand linear maps. We have one distinguished involution. How complicated can it get? It's incredibly complicated, and there are still many open questions about what you can get. Many open questions about infinite subgroups of the Cremona group, but let's focus on the finite ones. So if you just look at the first piece, automorphisms, well, it's a classic, early in 20th century, Blichfeld figured out what finite subgroups of PGL3 are. And again, it's sort of very symmetric shapes and so on and so forth. How about PGL4? Well, that's also in a thick book. And well, then the next thing you could ask, how do you, what are the finite subgroups of the Cremona group? So we understand finite subgroups of PGL3, PGL4. What about the Cremona group? So an enormous literature already in dimension 2. And of course, classical references, people looked at involutions, trying to classify involutions. It's very hard already. There are moduli, it wasn't complete until 2006, actually, all the involutions. So, and then Bouville and Deffernex looked at cyclic groups. Blanc-Cesis settled all abelian groups. It's beautiful 200-page thesis. I'll show you some results from it. Simultaneously, Dolgachev and Oskovsky, the result of 30 years of work, provided a classification of conjugacy classes of finite subgroups that can occur in the Cremona group, that do occur. Well, the initial table wasn't complete, follow-up work by several other people, but so here is an example. So here are abelian actions on cubic surfaces. This is what can act on a smooth cubic surface. And so how do we read the table? It will give us equations, and it will give us the action, and that's it. All right? So here the assumption is that it's minimal, that you can't simplify it by blowing down some orbits of curves, so that minimal actions. Now here is an example of an action. So on the function field on x, y, z, you look at this group, z2 plus z4, and the theorem of Blanc is that it's not conjugated to any subgroup of PGL3 acting on P2, or PGL2 times PGL2 acting on P1 times P1, acting on a quadrant. Okay? Well, that action is not stably linearizable. No fixed points. Now, in an abelian group, if it's linear, then there are fixed points. And so the theorem of Blanc from 2006 is that suppose you have a finite abelian group, I should have written abelian, assume that no element of G fixes a curve of positive genus, and in particular that H1 would be 0 for all G, yeah, then either the action is an action on P2 or P1 times P1, or it's the action of Z4 plus Z2 as I wrote down. So it's this kind of classification that the big result of this thesis. So let me talk a little bit about Dolgachov and Duskovsky. So how do they go about classifying all possible subgroups of the Cremona 2? Well, they use the equivariant minimal model program, like the Italians, reduce it to the case of Delpezzo surfaces or conic bundles over P1. And then, well, they just look at what possible transformations can you have if you have these kind of surfaces and these kind of groups acting. And the bottom line is that the degree is small if you're on a cubic surface, and there's nothing you can do to make it sort of simpler. The action is rigid and comes from, or you see the action via the action, it's some subgroup of the induced action on the Picard group. So in other words, you just have your G represented as a subgroup of the automorphisms of the primitive Picard, which is in the Weil group, cubic E6, E7, E8, and so on. And so the resulting analysis is you get long tables. You look at all possible subgroup of the Weil group of E6, and you see, can this group be realized or not on in real life? And so this is a complete table for cubic surfaces. And of course, you can see the diagonal one that's at the top. Well, you can permute the coordinates, that's the S4 action. And then, of course, you can twist multiplying by the third root of 1 each of the coordinates. And because it's projectively, it's, only Z mod 3 cube survives. And that's what you have. And then there are all the other ones. So these are the normal forms for all the actions that you can have. Okay. Well, and otherwise, you find, things to blow down, and you can blow down until you hit P2. And now you have an action on P2. And as I told you, we know the finite subgroups of PGL3. We know what acts on P2. What is it that we don't know? Well, now we have no idea whether or not given actions on P2 are equivariant birational. And that's still open. It's still an open problem. Amazing. Now, so how do we distinguish equivariant birational types of linear actions? Forget, cubic surfaces and so on. And how do we distinguish linear actions from nonlinear actions? So I will now review some invariants, define new invariants, show you some applications. So to work over a field of characteristic 0 and algebraically closed, we don't need this. All we need is roots of unity in the field. And which roots of unity? The order of the group plays a role. The order of our finite group. So we have a finite group. We look at the smooth projected G variety. And most of the time, without the G action, it will just be PM, because we want to understand the Cremona group. And to look at fixed points. So the basic facts here are, if the group is cyclic, you are guaranteed to have fixed points. If the group is abelian, then fixed points, yes or no, is a birational invariant. And the standard example of an action of an abelian group without fixed points, of course, is a Z2 plus Z2 action on P1. X goes to minus X goes to 1 over X. There are no fixed points on P1. Now, it turns out that once you have a fixed point, then you see in the tangent space the full group action. So in a vector space over your ground field, you can diagonalize your action. So if G is abelian, you pick up characters of your abelian group in the tangent space. And what can you do when you have characters? You can take the determinant for the action. And so a result of Reisten and Houston says that that determinant up to plus minus 1 is an equivariant birational invariant. So not only the existence of fixed points, and you have an abelian group action, but also the determinant for the action. And so that gives you examples of representations that are not equivariant to each other, but well, any representations will be equivariant, stably equivariant. So cyclic actions on Pn for n bigger or equal than 2 are all equivariantly birational. Why? Because it takes the determinant, you get 0. So to get something non-zero, the rank of your abelian group has to be equal to the dimension. So, and you get examples of non-birational but stably birational actions, linear actions. Let's be very concrete. So let's look at the action of Z mod P on P2. How do we act? We multiply coordinates as piece roots of unity, just like you do. And well, we don't want to multiply with 0, 0. We want some kind of non-trivial generator there. So we have, AB. And what are the fixed points? Well, the fixed points, of course, are standard coordinate fixed points: 1, 0, 0, 0, 1, 0, and so on. What are the weights at these fixed points? Well, you see it in the tangent space. Well, you see it right away. AB, so you just record AB, residue mod P. And then when you look at the other fixed point, you have sort of to rescale. So when you rescale, you see A minus B, and then you see B minus A. So those are the three things that you record. Of course, when you record these weights, AB is equal to BA because you don't know what's first, what's second. And well, so since we know that all these actions are equivariantly birational, we may declare that they're all equal, and in particular, let them all be equal to 0. So let's take that difference, AB, like this symbol minus that symbol, to be 0. And now allow for the sign to go in and out of this symbol. You get this some relation. And then we find the relation AB is equal to AB minus A plus A minus BB. And let's impose this relation and see what happens. So we look at pairs of residues mod P, AB equals BA, and satisfying this relation. And it turns out that the Q rank of the vector space on these generators subject to these relations is P squared minus 1 over 24 plus 1. 24, where does the 3 come from? Of course, when you say AB equals BA, well, the 2 you can kind of think that you can account for it, but the 3, 24, well, it turns out that this thing is connected to the modular curve x1 of P. It's just the dimension of the first homology, this terms of Q. So then with Q coefficients. Well, that's kind of surprising. Now, it's sort of interesting. That's what it is. So we continue the investigation sort of more generally. We look at the arbitrary finite abelian group. Let A be the group of characters. Let's look at the regular G action of some variety and decompose the fixed point locus into irreducible strata and record the weights in a tangent space and write down this map from variety with a G action to some of these formal symbols and keeping no information about the strata themselves. And now consider the group spanned by these symbols, unordered tuples of characters of your group, subject to the condition that they generate the group, because otherwise, well, And so you get a map from G varieties to the symbol group. And then you want to produce an equivariant birational invariant. In particular, you want this thing to be invariant when you blow up equivariant. So you look at some equivariant blow up and you impose relations. Nothing is supposed to change. Well, there are many blow-ups that you have, but it turns out that you can encode these relations in a very complex form, and that's the form. The relation that I showed you for P2 is actually universal. Once you impose this relation, A minus BB and A B minus A, doing nothing to all the other entries in the symbol, and then simply using the symmetry Sn, well, you get an equivariant birational invariant. These are very interesting, as I told you in for Z mod P and n equals 2, you get this interesting formula. But how about the next one, B3? Well, B3 is P minus 5 times P minus 7 over 24. And you plot it for the first couple of primes, and you say, wow. And then suddenly you find jumps at 43, 59, 67, and so on, sometimes by 1, sometimes by 2. So it turns out that the proof is, again, this is related to homology of arithmetic, certain congruent subgroup of GLNZ in complete generality. So, but again, these are the groups that are going to capture the invariance for actions of abelian groups. And of course, as before, you can introduce a Gaussian, then you move the sign in and out. And once you have it, you find that actions on Pn by cyclic groups are torsion in the Bn and trivial in Bn minus. Okay, so motivated by this, you wanted to look at non-abelian groups. What happens for non-abelian groups? So now you also want to take into account the geometry of the strata with non-trivial stabilizers. In other words, now the groups will be generated by symbols H, Y acting on some field and beta. H is an abelian subgroup of our non-abelian group G. Y is a subgroup of the centralizer of H modulo H. K is a certain function field. It's a function field of the stratum which has H as a generic stabilizer. It will have transcendence degree of n, the dimension we're looking at, and beta is a sequence of characters of the stabilizer in the normal bundle to the stratum that we're looking at. So this is where the action goes. And there are, of course, some relations. So our first relation, we are in a non-abelian group. As we go from one element of the orbit to another, the stabilizer changes by conjugation, because you don't want to distinguish a choice of an element in an orbit. Well, you just consider everything up to conjugation. And of course, once you have conjugation, you add an action on the stratum. When you pass to the next one in the orbit, it's sort of conjugated orbit. And then there is also conjugation action on the weights in the normal bundle. So that's trivial, sort of the conjugation relation. Then there is a trivial blow-up relation, which says that if two eigenvalues in the normal bundle add up to 0, then that symbol disappears. But the non-trivial blow-up relation is this one. You take a symbol, and it's a sum of two terms. The first term is just like the one we saw for abelian actions looking at fixed points. Namely, you only change the first two entries, b, b minus 1, 2, b, b2 minus b1, and then b1 minus b2, b2. That's the things that you change, and you leave everything as it was before. And the second term, which is non-zero under some circumstances, replaces the action, replaces the stabilizer. And how do you understand what happens there? You just take a surface, as an isolated fixed point, you blow up. The first term gives you the contributions from the fixed points on the exceptional divisor. And then the second term, theta 2, is a contribution from the exceptional curves that could also have a non-trivial stabilizer. And well, you see K of T, that's sort of an extra transcendental variable that's added to the middle thing in your symbol. And then there is some sort of an induced action on it and corresponding characters in normal bundle. You have to really, do some examples. But when you look at our paper, you see it's pages and pages of combinatorial simplifications and so on and so on. You compute the class on some model. What you want from the model is that there is this risky open U, the boundary normal crossings, the action on U is free, but for each component of the boundary, either the translate of the component is disjoint from the component or equals to the component. So this is called the standard form. You can reach it after an equivariant blowup, and that's where you compute your class. And then, how do we compute the class? You write down a sum over abelian subgroups up to conjugation, strata with those stabilizers, some kind of action in the stratum, and beta the corresponding characters. And the theorem is that this is a well-defined G-equivariant birational invariant, just like in the previous case. Now, it's complicated. However, you can sometimes simplify it. Namely, there is this notion of incompressible divisor symbols, namely symbols H, Y, and K, where the stratum is a divisor. It's a one-dimensional one. Necessarily, beta only has one character, and what you want is that that symbol never shows up in a theta 2 term in the defining relations. And that you can actually check. In dimension 1, those incompressible symbols, because they're not involved in any relations, they're just free. There are no relations between those symbols, and there are no relations between those symbols or anything else. Your Burnside group, as you call it, splits into direct summons, and therefore, if you can distinguish action upon projection onto one of those direct summons, you're done. So in dimension 1, every symbol is incompressible because there simply aren't any relations in dimension 1. As I told you, birational maps are all isomorphisms. But in dimension 2, there is a characterization. A divisorial symbol, which means that in the middle you have a function field of a chord with some action, is compressible if and only if the action Y is cyclic and the field is a function field of P1. And so that gives you a collection of incompressible symbols. Now let's go back to our problem. How do we distinguish up to birationality actions on P2? So, well, the classification of finite subgroups of PGL3, how does it work? Well, you look at linear representations. If it splits into one-dimensional plus two-dimensional, well, or a sum of one-dimensionals, then if it's reducible, the action is called intransitive. If the representation is irreducible, but upon restriction to a normal subgroup of your group, it becomes reducible, then it's called imprimitive. And in other cases, it's called primitive. So the analogs of primitive actions for PGL2, P1 is like the A5. Now, intransitive, because representation decomposes, you can view your group as sitting in K star times GL2K, some finite subgroup. And we already know what the finite subgroups of GL2K are. You take subgroups of PGL2 and you lift them to GL2. And well, okay. So you have subgroups that we looked at. And the other case, the transitive pattern primitive, you should visualize as action on P2 minus the 3 lines, which is an algebraic torus, and you can do translations in the torus, and translations in the torus is simply multiplication by roots of unity of the coordinates. And then you can permute the coordinates. So this is a permuting the 3 lines and the 3 points on P2. That's a transitive and primitive action. Okay. And the other actions, they're all listed here, A6, P2F7, A5, and so on. That's it. Those are the actions on P2. Now, how do we distinguish them up to equivariant birationality? H1 is not going to do anything because Pn, the Picard is Z. So H1, this coefficients in Z is trivial. The way algebraic geometry approaches this, they try to do birational rigidity in presence of group actions. And the theorem from 3 years ago says that you can actually understand those primitive actions. So birational rigidity means that there's nothing you can do. That given the action, it can fix and rigid. So, and this allows you to actually classify up to birationality those kind of actions. There are 2 actions of A5. There are 2 3-dimensional representations of A5. They are not conjugated in PGL3, but they happen to be conjugated in the Cremona. On the other hand, there are also two actions of PSL2F7, but that action is super rigid, and so those are not conjugated in the chromonomy. Okay, so that's the outcome of this. So it's not trivial. So it settles that class of actions. Now the transitive and primitive actions, well, they contain an abelian subgroup of rank 2, you know, the torus, the translations into torus. So sometimes you can use the Reichstein-Houston criterion to distinguish them, but not always. So I skip that. So the most interesting case from the perspective of like equivariant geometry and our perspective is that remaining class of intransitive actions, where the action goes through some cyclic group times a subgroup of GL2. And so, well, here we can deploy the new invariants that we have introduced. And the way we do it, we just take a two-dimensional representation of our favorite group, you know, the subgroups of GL2, and take a one-dimensional representation of a cyclic group. We get the generically free action of the product cyclic times a subgroup of GL2 of interest on your projectivized one-dimensional plus a twisted two-dimensional. We need to bring the action to the standard form. Because of the special shape of the action, trivial plus two-dimensional, we have a fixed point corresponding to the trivial piece. And the fixed point, of course, will have a non-abelian stabilizer. So when we compute our class, we need to blow up that sink. When we blow up the sink, what we find is a symbol, the stabilizer, that cyclic group Cn, times the G prime action on the function field of P1, the exceptional divisor was at fixed point. But we also have the projectivization of that representation, that V of epsilon. So that's another class that now is recorded with a different character, this minus character that we used to twist our representation, the character of the Cn. The bottom line is that if you choose epsilon and epsilon prime so that they don't agree up to plus minus 1, then the contributions from those two terms to the class, these are incompressible symbols, they're really different. And so this allows us to distinguish actions. Now you would say, okay, P2 is easy. In principle, we can start, you know, blowing up, blowing down until we're done. But we have a similar theorem for P3. And there it's totally hopeless. Nobody knows how to really factor, you know, effectively things in dimension 3. And again, looking at subgroups this time around of GL3, for example, PSL2F7, looking at these kind of representations, twisting by characters of cyclic group Cn, and again, looking at projectivizations of trivial plus a twisted three-dimensional representation, and again, computing the classes, you again get these kind of terms. And well, if epsilon is not equal, you know, to epsilon prime up to plus minus 1, these incompressible symbols distinguish those actions. Okay. So the last thing I wanted to say is that, you know, we focused on linear actions, but the study of nonlinear actions is also very interesting. The study of rationality in dimension 4 is very interesting for the following reason. It's very hard to, you know, have an explicit sort of minimal model program or some explicit factorization of birational maps in high dimensions because it's so hard to control what you can do. You have varieties, sub-varieties, blow up, blow down, totally unclear. So in particular, cubic fourfolds, there is 3 equations, E5. You know, there are rational examples. The conjecture is that's a very general one. It's not rational. Anyway, it's sort of a major open problem. Again, many papers on this subject. Recently, there is sort of a completely new approach to the study of rationality. Quite sophisticated invariants of derived categories, you know, play a role and so on and so on. Now, we wanted to be concrete. So let's look at this problem in presence of group actions. So I'm looking at this particular cubic fourfold, and it happens to have an action of Z mod 36. So, well, where are the fixed points? So the fixed points, of course, are, again, I'm not allowed to take 1, 0, 0, 0, because x0, you see, is isolated there. So I'm going to take 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. I mean, the fixed points are staring you in the face. that are sort of at the corners. And I need to compute weights. So I'm looking at the first fixed point, like this one. So to compute the weights, well, the actions, the weights given at x trivial and x zero. But now I have to rescale to go to the affine chart. So I'm rescaling. I'm writing like -4. I'm putting the weight 0 on the coordinate x1. And then 24 minus 4 is 28 minus 4 is 24, and so on and so on. Then I need to compute the tangent space. The tangent space means that I'm going to throw out the second coordinate, and I'm going to throw out the other one, there x2 equals 0. And so I'm left with the weights -4, 12, 5, and 14. And then, of course, you know, tangent, cotangent, who knows? I mean, like -1, I have to do it consistently. And I pick up such a class. This is my class. Boom. My 4 tuple. And I do it at all the other points, and I take a sum. And I want to view this sum as sitting in the element B4 of D mod 36. And I compute. And there are 400,000 linear equations and 82,000 variables. It's totally unclear. It's highly overdetermined. It's not even clear that this thing has any non-trivial solutions. But it turned out that the space, it has 2 torsions. It's like F2 to the 19. And as I told you, cyclic actions on projective spaces in higher dimensions are all the same. And the class is either 0 or torsion. In this case, the class is 0. But the class that I've computed here, after solving all of these equations, is actually non-zero in the group F2 to the 19. So the classes are non-zero. This action cannot be equivariantly birational to a linear action before. So, well, that is to show you the kind of how these invariants work, and they're quite powerful. Now, again, to focus your attention on this, the classification of linear actions of fine groups on P2 up to birationality is still open. Our invariants allow to cut down the pool, but we cannot tell when, by some accident, the classes are equal in the Burnside group. Are these actions actually birational? We don't have an if and only if. We only have more and more examples of non-birational actions that were not accessible before. And finally, well, there are these new invariants that appeared, and they offer new approaches to, you know, these standard classical problems. And this is it. Thank you so much.
Thank you very much for this. So, any questions?
Are chronological techniques ever useful, export formulas, things like that?
Chronological techniques are useful to chronology, how chronology plays a role. We showed that in dimension 3, the new variants get introduced, and chronology are orthogonal. So there are examples that distinguish actions using our invariants and are indistinguishable chronologically. And there are also examples that we cannot distinguish, but chronology will distinguish. The way we view these invariants, taking into account fixed or loci and we think is some kind of Atiyah-Singer localization. Except that in Atiyah-Singer localization, what's recorded is a determinant of the action normally. We record all eigenvalues. So, and then introduce these kind of relations. So this is to be explored further, but there are connections, but it's not the same. It's not, definitely not the same. Yes.
Can you say more if you assume that the actions preserve some initial structure, for example, preserve an elliptic vibration?
Well, I thought that the end of the sentence would be preserved volume 4, for example. Yes, that's very interesting. And then we expect that it will be some symplectic symbols will connect to longer subgroups, not in G and Z. In terms of preserving certain geometric structures, well, yes, we have those formulas. We have variety, this can be action, and you have a G vector run over it in the projected lines. You may want to compute the class of the utilization of a vector of the global thing in terms of the classes of things that you see on the base and on base this direction. And we do that. We have close formulas for that. We do explore some geometric. Now, elliptic vibrations are not so interesting from the perspective of Birational geometry. Anyway. Rather look at projectization vector. Yes.
So some examples where data is explicit. How about the non-commutative case? Are those variants can be computed?
Oh yes. So what we did, a paper from this year, with Andrew Crash, you look at. So when you do representation theory, there's something called the character. So and they determine the thing capital I wanted. So we have some closed formula and algorithm for computing class of projectization of linear action. In terms of well, strata, there's no trivial stabilizers and the whole combinatorics. And this is an equivariant version of the Cauchy-Purchasing, wonderful simplification of components of subspace arrangements. It's complicated, it's combinatorial, but my students and my graduate students have implemented this in Magma. And so you give a representation and you split out a class in form formula. And then you have to check whether that is equal or not equal to some other class. Yes, a lot of experimental information, many examples. Yes, and we also do it for actual toric varieties. Same thing, Gini projected toric varieties. So the answer is yes, you can compute the classes, the computation of equivalences is very non-trivial. It's easiest if you can distinguish them by incompressible symbols, but we have plenty of examples where incompressibles don't give you the difference, but the others do. It's the one I just showed. All right, and I think we need to go on to the next one because
Just one more remark. When we say math is everywhere at the time of the conference, no one should actually is in robotics, in computer vision at least. But you maybe didn't know that the cubic formals appear in models of complex systems, in models of smart cities. Did you know that? No. But it's nice to know.
Yes.
Okay, we have a very tight day, so we don't have a break. And we are just calling, okay.